Now that we completed the simulation of different types of transformer using Plex, it's time to look into where we can use this type of phase shifting transformer for the converter implementation. Here is a typical use of that phase shifting transformers that we saw during our previous simulation. For example, we have to implement here a rectifier that is 18 pulse. For that, we need to have a phase shifting transformer with 3 secondary windings. Now, if we want to implement an 18 pulse rectifier, we need the phase shifts between the primary and secondary side of the transformer, here as specified, 20 degrees. Now, why 20 degrees? It's 60 degrees divided by the number of P6 bridges. For example, if we have 12 pulse rectifiers, then we would have the phase shifts between the primary and secondary side of voltages 60 divided by number of bridges, which is 2, that would be 30 degrees, as we saw in one of our previous videos. For this specific case, since we have 18 pulses, we have 6 B6 bridge, 3 in serial connection. That means 60 degrees divided by 3 is then 20. Now, in order to introduce a phase shift of 20 or any number, we saw from the previous tutorial that a Z transformer or zigzag transformer is required. So it is shown here. We can implement easily minus 20 degrees, and between star and star there is no phase shift here. And to the left we have plus 20 degrees of phase shift. And these 3 bridges, bridge 1, bridge 2 and bridge 3, they are connected in series. On the DC side of the rectifier we may have RL load or R load depending on application. On top of the screen we have the grid. Let's go to Plex and implement the circuit. As we are now still on the preliminary phase of the design of converters, I will simply take the Plex inbuilt P6 bridge here. That means I do not consider the detailed modeling of diodes or snapper circuits, etc. So here you see the diode forward voltage 0, on state resistance is 0, and the same for all 3 serially connected converters. Here this represents the source or grid, as I just showed you in this single line diagram. Since now these variables I set it in M file so that I can change it as I want. So I chose a primary high voltage side voltage to be 10 kilovolts. This can be different depending on different applications. I take a grid frequency of 50 Hz, also specified as a variable, and this completes the modeling of the grid side source, so to speak. Now the factor square root of 2 by 3, as you already know, since we are specifying the amplitude of a single phase, so to speak, it takes as a single phase, but we want to have as an output a 3-phase line-to-line voltage. The factor of square root of 2 by 3 is introduced. Now, since we do not have a standard transformer in Plex with 1 input, 1 primary side and 3 or 4 or more number of secondary sides with exactly this type of configuration, what I take is 3 different Star-Z or Star-Zigzag transformers. Let me show you. If I go and select transformers, you see we need to choose either from this one, YDY or YDZ, which doesn't really serve our purpose here. So a small trick would be just to take, for example, Star-Zigzag transformer or zigzag, depending on your choice. I took this one, Star-Zigzag, and then change the values to get the corresponding voltage levels and phase shifts on the secondary side as here. Let's check the first transformer. I put it somewhere it's a good place. Now I defined the leakage inductances and resistances as variables here, which I wrote here in the script as well. And as you saw from the transformer video, that we need to specify in the dialog box the winding ratio of the transformer, not the turns ratio. But since we're dealing with a transformer with vector group Star-Zigzag, it is exactly same to the turns ratio as I mentioned here. That means I can take on the primary or high voltage side 1, and since we are stepping down the voltage, which is 1.5 kilovolts in our case, we divide, or we take the inverse of the turns ratio, or winding ratio to be more correct. Other parameters like magnetizing current values or magnetizing flux values, we leave them as default because we're not considering, as I mentioned before, the detailed configuration and modeling of the converter. Now this is important, as you saw, that we need to introduce 20 degrees phase shifts for each secondary side. I take a phi variable 20 degrees, and here in the transformer properties we can input this value phi. Now the description says it's phase lag of secondary side, so we can take it's minus 20 degrees. For the second one we will introduce no phase shift, other parameters are same. And for the last secondary side, that is, we need to introduce minus phi because we want to have a leading 20 degrees, a positive 20 degrees of phase shift. So I write it minus phi. For measurements, I take 3 phase meters on the primary side and 3 phase meters for 3 secondary sides. Give the measurement to different scopes. I measure the high voltage side voltage, secondary side voltages, DC current and DC partial voltages, and DC final voltage in the scopes. I leave the load as resistive load, but I will connect it later once I validate if the connections are giving us the correct results. To run the simulation, as always, I take this command sim followed by the name of the simulation file. You can just read the name or also with an extension SLX representing the simulation file. I have, for better calculation results, I have this maximum time step to be 10 microseconds, and I simulate it for 5 periods for 50 Hertz grid. Now inside the simulation parameters, I said this is our simulation time, which is 5 times 20 or 100 milliseconds. I take Dormant Prince ODE 45 solver. For refine factor, I take 5 so that the curves are shown with precision. Now we are ready to simulate. Let's run the project. Let's check the values. Now at this point, look, we do not connect the resistive load yet because I want to see in the normal operating mode, that is open circuit conditions. Now we activate the cursors to measure the voltage. So first one is the high voltage side curve, and the other 3 secondary voltages are following. I'll take a period here. The 2 cursors place exactly at 20 milliseconds apart. And then if we measure the RMS voltages, they're 10 kilovolts as we specified, and 3 remaining secondary sides are having 1.5 kilovolts. Now the phase shifts can also be noticed here if I take a little bit zoomed view. So first one is already set here. The secondary we're expecting, the first secondary we're expecting a 15 degrees lagging phase shift. 15 degrees lagging phase shift means we have 0.83 milliseconds. So if we put it here, adjust a little more, you see here between first and second green curves here, we have around or approximately 0.83 or 0.84 milliseconds. For the third curve, we had star-star connection, so here we have no phase shift. And for the third one, we have a leading, was it 15 degrees? No, it is 50, it's not 15, it's 20 degrees. I made this mistake. So let's see, it's around here. And if we calculate, let's check if it is 20 degrees. So I apologize for the confusion here. I forgot that it is 18 pulse rectifier. So if you put the cursors to the correct position, we should see around 20 degrees phase shift, which represents 1.1 milliseconds. So if we see here between first and second blue curves, we have 1.1 milliseconds delta. And if we take the first and third curve secondary, that means here we will have a leading phase shift 1.1 milliseconds is exactly here. It's 1.1 approximately. So the settings are correct for the grid voltages. And on the DC side, since we have no load, the current is 0, not a wonder. And then for the voltages, so the first three are the partial DC voltages at the output of, or the DC side voltage of 3 B6 bridges. And on the bottom, we have the total DC voltage. This total DC voltage should have 18 pulses in one period. That means if we take 20 milliseconds, we can write 0.02 here and check and position it somewhere reasonable, like here. If we count each partial DC voltages, it should be 6 pulse because they are all 6 B6 bridges. So if we count 1, 2, 3, 4, 5, 6, and also same for the other two. Now we want to count the number of pulses for the complete DC voltage. So we start here with a 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, and 18. So we are getting the expected DC voltage levels from the serial connection of the B6 bridges. If we connect the load, for our case it was our DC, and the variable is specified here as 5 ohms. Of course, it will vary depending what sort of application we have. Let's rerun. Now we're expecting to see some sort of distortion in the grid voltage as on the secondary side, or I should say more specifically the converter connection voltages. You see there are some distortions here on the voltages. Now these are the result of the input side inductance resulting from the converter. This is the commutation effects. If we now look into the current, we will see the ripple current here. Again, this is depending on what type of application we have. If we measure the DC current level here for our 5 ohm load, let's measure it. It's 1.2 kilo amperes. It also has the same number of pulses in a space of 20 milliseconds. And these are again the voltages. As we can see, the effect of current flow and the effect of source inductance both are reflected on the respective curves. So in the detailed, maybe in the future videos for detailed calculation, we'll also exactly calculate the grid impedances, the transformer impedances, the reverse recovery effect of diodes in the bridges, and also effective and short circuit conditions. What happens, for example, there is a DC short circuit, or maybe single phase line to ground fault conditions. We will explore them in our future tutorials. Thank you for watching.